This is part one of the series Quadrilaterals. In this series, we're going to talk about many different types of quadrilaterals, their properties, and their relationships. And we're going to look at how to use them in solving problems. So let's first start out with polygons and interior angles. Remember that interior angles were the angles formed by adjacent sides of any polygon. And we talked about the sum of the measures of the interior angles of a triangle. And we looked at the fact that the sum of the interior angles of any triangle add up to 180 degrees. And we looked at that theorem and the proof of that theorem. Now we're going to look at a general polygon and the sum of the measures of the interior angles to see how those relate. So here is a regular polygon. A regular polygon is a polygon that is both equilateral and equiangular. Remember that these words mean equilateral, all sides are congruent. Equiangular, all the interior angle measures are the same. All interior angles are congruent. Now, if I wanted to draw a segment from one vertex to all of the non-adjacent vertices from that one vertex, I would actually create other triangles. These segments connecting the non-adjacent vertices are called diagonals. A diagonal is a segment connecting two non-adjacent vertices. So here we have 1, 2, 3, 4 triangles. Notice that this regular polygon has 6 sides. So this is a hexagon. And by drawing all the diagonals from one vertex, we created 4 triangles out of those 6 sides. So the relationship here is there were 6 sides and 4 triangles. Now you know that the sum of the measures of the interior angles of each one of these triangles is 180 degrees. In case it's not perfectly clear what's going on here, this angle plus this angle plus this angle equals 180. This angle plus this angle is the measure of that interior angle. This angle plus this angle is the measure of that, and so on. Therefore, if we add the sum of the measures of these interior angles with these, and these, and these, we will get the sum of the measures of the interior angles of this regular hexagon. So that's all we have to do is take the number of triangles, multiply it by 180, and we have the sum of the measures of the interior angles of this polygon. So that relationship is summarized in the following theorem. This is the polygon interior angles theorem, and it states the sum of the measures of the interior angles of a convex polygon is 180 times n minus 2, where n is the number of sides in the polygon. So here again we had 6 sides. 6 minus 2 was 4 triangles. 180 is the sum of the measures of the interior angles of each one of those triangles. So it's 180 times 4, which comes out to 720 for this. So that's the polygon interior angles theorem. Let's go ahead and work an example using this theorem just to make sure we've got it down. In this example, we have a convex polygon, and we want to find the measures of the interior angles of this polygon. So we have 1, 2, 3, 4, 5, 6, 7. So this is a heptagon, 7 sides. So our formula then is the sum, that's the Greek letter sigma, stands for summation, equals 180 times n minus 2. Our n is the number of sides, so this is 180 times 7 minus 2, which is 180 times 5, which is 900. So the sum of the measures of the interior angles of this 7-sided polygon is 900 degrees. And let's move on to the next piece. Here we have the corollary to the polygon interior angles theorem. If you remember, a corollary is a theorem that can be proven using another theorem. In this case, this theorem follows directly from the polygon interior angles theorem. The sum of the measures of the interior angles of a quadrilateral is 360. And we know from what we just saw from the polygon interior angles theorem that the sum is 180 times n minus 2. And if we have 4 sides, that's 180 times 4 minus 2, which is 180 times 2, which is 360. So a fairly obvious theorem, but nonetheless, as we've seen many times in geometry, this is a discipline of details, so we have to go through it. Polygon corollary to the interior angles theorem. So let's move on to the next piece. Here we have the polygon exterior angles theorem, which says the sum of the measures of the exterior angles of a convex polygon is 360 degrees. Now, remember that an exterior angle is an angle that is a linear pair with an interior angle of that polygon. You just extend a side of the polygon and you create an exterior angle, and the exterior angle and interior angle pair are a linear pair. And as a linear pair, these are supplementary angles. So in this case, this one's 60, this one is 120 degrees. And it's that linear pair relationship that forms the basis for this theorem. So let's take a look at the theorem and step through it real quick. We'll start with the polygon interior angle sum theorem, which is 180 times n minus 2, where n is the number of sides. An interior angle, any one interior angle of this polygon, is given by the sum of the measures of the interior angles here divided by the number of sides. So take the total of the sum of the measures of the interior angles, divide that by the number of sides, and you come up with one interior angle. Now remember that an exterior angle is supplementary to that one interior angle. So the exterior angle is going to be 180 degrees minus the measure of that one interior angle. And we substitute this expression for the measure of that one interior angle, because this was the measure that we calculated for the interior angle. And 180 minus this expression gives us the measure of one exterior angle. If we look back at our picture here, we can see that there's one exterior angle for every side in our polygon. And because of that fact, we know that the sum of the exterior angles is going to be given by the number of sides times the measure of one exterior angle. And since we have an expression here of the measure of one exterior angle, we come up with the number of sides times this expression, which is the measure of one exterior angle. Now, working through the algebra, we distribute this 180, so 180 times n is 180n. 180 times negative 2 is negative 360, and we just carry down the division by n. Now what I did in this next step, from here to here, is a very common algebraic approach for getting a common denominator with two fractional components. So just really quickly over here, if you have something like 3 over 5 plus 2 over 4, and you want to get this into a common denominator form, that's all you have to do is multiply this by this, so that's 12, this by this using this sign, so that's a positive. 5 times 2 is 10, so that's plus 10, over the denominator product, this times this, 20. And that gives you 22 over 20, which of course can be simplified. But the important thing is that you got from two fractional components, you got one rational expression with a common denominator. So that's what I did here. I took this and multiplied it by 180, so 180n. This is 180 over 1, so 1 times this numerator gives us that same numerator because we're using this sign. So it would be 1 times negative 180, which is negative 180n. 1 times negative of a negative 360. Negative times a negative is a positive 360. So that's how we got this expression. Now you can see that this outside n is being multiplied by this expression, and that cancels out with this inside n. So n divided by n is 1. We have 180n minus 180n. That goes away to 0, and we're left with the original 360. So this is where the polygon exterior angles theorem comes from. As with most of the videos that I've done, I present these proofs here in case you're interested in finding out where these come from. If you're just interested in the theorem itself, please feel free to skip this and move on to the next step. And you can do that with all the proofs that we're going through. But if you're interested in where these things come from, and if you may happen to need to do the proof yourself, perhaps you're in an advanced course, then these should prove helpful to you. So let's move on to the next section. Here we have an example where we're looking at the exterior angles of this polygon, and we're given some expressions and some values for these angles, and we want to find the value for x. So we've learned that by the polygon exterior angles theorem that the sum of the measures of all these angles is 360 degrees. So let's go ahead and use that to solve for x. We have 360 equals 2x plus x plus 67 plus 89. So that gives us the sum of our exterior angles. Let's go ahead and combine our terms. 360 equals 3x plus 156. We'll subtract 156 from both sides. 204 equals 3x, and 68 equals x. And you can cross-check. If you plug that back in, you can see that 68 plus 67 plus 89 plus 136 comes out to 360. So let's move on to another example. In this example, we need to find the measure of each interior and each exterior angle in the regular dodecagon. Now, a dodecagon, remember, was a polygon that has 12 sides. So now the easiest way to do these is to use the exterior angles theorem to figure out the interior angle theorem. Remember that the sum of the measures of the exterior angles is 360. So if all the angles together is 360, and it's a regular dodecagon, meaning that all the angles are equal, then if we divide 360 by the number of sides, we'll get the measure of one of the exterior angles. 360 divided by 12 is 30. So here we have, if we take a look at this one here, we have an angle going up like this, and this is 30 degrees. So this exterior angle here is 30 degrees. Now the exterior angle and interior angle make a linear pair, which of course are supplementary. So we know that this angle has to be 150 degrees. So the measure of each interior angle is 150 degrees, and the measure of each exterior angle is 30 degrees. As a quick cross-check using the sum of the measures of the interior angles theorem, the sum is 1800, and if you multiply 150 degrees times 12, you get 1800. So let's move on to the next section.